Good morning. Today I would like to discuss about the building blocks of the FPGA. So previously we have discussed about what are the different types of boards we are going to consider. One is the VHDL system 3 and another one is RT. So in both the boards the same FPGA family is there with similar properties, that is already RTX 7 XC7A35T. That is the family of FPGAs are available in both the boards. Okay, so whatever the FPGA in general, the building blocks are, okay, so here is the slide showing 9 different blocks. So usually these 9 different blocks you can observe almost in any type of FPGA. Those are IOBs. IOBs means input output blocks. IOB means input output block. CLB. CLB means configurable logic block. CLB means configurable logic block. Then interconnect resources. Interconnect resources. RAM block, DSD slices, clock management, XADC, it's not DAC, XADC, that is analog to digital converter block, high speed serial IO transceivers, high speed serial input output transceivers, PCIe interface, that is peripheral component interconnect express. So these are the 9 different blocks usually you can observe on the FPGAs. Okay, so these are the different basic building blocks like you can consider in the FPGAs. Coming to IOBs, that is input output block. So what it is means, it consists the number of pins act as an input and output. That is, through these pins the FPGA can connect with the outside world. That is, it can accept the data from the outside world through these pins, or it produces results to the outside world through these pins. Okay, so usually these boards FPGA pins can accept 1.2 to 3.3 volts as a logical voltage level, and if you come to base system 3, it has 106 such input output pins, whereas in RT boards totally we have 210 input output pins. So these pins can be used as input to the FPGA or output from the FPGA, or sometimes both. Input to the FPGA means the FPGA can collect the data through the input films from the outside world to FPGA. Output pins means the FPGA can give its results to the outside world through the output pins. Both means some pins acts as the input and also output. And these input and output pins are grouped into bags, and in each bag 2 pins are grouped as positive and negative pairs. And the modes of operation of these pins as single-ended mode, differential mode, sometimes reference mode also. In single-ended mode, the input will be recognized as logical 0 when the input voltage level is nearer to the ground. Similarly, the input is recognized as logic 1 when the input voltage is nearer to VCC. Whereas in the differential mode case, the input will be recognized as logical level 0 when the voltage at pin P is lower than the voltage at pin N. P represents the positive, N represents the negative. Otherwise, it is considered as a logical high. That is, if the voltage level at pin P is greater than the voltage level at pin N, that is considered as logical high. Similarly, in the reference mode case, the input will be considered as logical level 0 when the input voltage is less than the reference voltage. Otherwise, it is treated as a logical 1. So, like that, the FPGA can interact with the outside world through these bits. Then coming to the block CLB, that is configurable logic block. It includes multipliers, flip-flops, lookup tables and slices. Okay, so the configure logical block, actually the digital circuit, whatever the digital circuit we are going to implement on FPGA is realized through these CLBs. Okay, these CLB blocks are the circuits which realizes the logic function, but it includes the multiplexers, flip-flops, lookup tables and slices. Coming to one by one, that is multiplexer. First of all, already we know that the multiplexer is a selector switch, a selector network, or you can say multiplexer is a selector network based on the selective data. The selected input is connected to output. In general, the multiplexer can be represented as 2 power n by 1. Is the size of multiplexer can be represented as 2 power n by 1. That means at the input it has 2 power n combinations. At the output only one is there. Only one output. And such a multiplexer has n select lines. So based on the select lines data, one of the 2 power n input is connected to the outputs. So here is one simple multiplexer diagram with the size 2 by 1. That is having 2 inputs and 1 output. Okay, and one selector line. In case of 2 by 1 multiplexer, the select line is 1, and this is the logic diagram using basic gates for this 2 by 1 multiplexer. So if you observe here, suppose if the select value is 0, okay, what will happen? Whatever the input 1 is there, that is connected to the output, because if the select value is 0, one of the input for the upper AND gate is 1. Whereas the second AND gate case, one of the input is 0. And also we know in AND gate case, if one input is 0, the output is always 0. Suppose if the one input is 1, the output of the AND gate is equal to the other input. So the output of second AND gate is 0, whereas the output of first AND gate is in 1. Okay. Now for the OR gate, one input is in 1, other input is 0. In OR gate case, if one input is 0, output of the OR gate is equal to the other input. Therefore, out equal to in 1. Okay. So if the select line data is 0, the first input is connected to the output. Similarly, suppose if the select line value is 1, the second input is connected to the output. Okay, clear? So that is represented here, out equal to in 1 when select value is 0. Output is in 2, that is second input, when the select value is 1. Okay, so like that the multiplexer can see the operation and realization. And coming to flip-flop, already we know the flip-flop is a 1-bit storage element. A 1-bit storage element. There are different types of flip-flops like D flip-flop, RS flip-flop, JK flip-flop, T flip-flop, like that. Okay, and each flip-flop we know that used as a memory element for storing the 1-bit data. Now coming to another block which you observed in the CLB, that is the lookup table. Lookup table. So what is lookup table means? It consists of flip-flops, a group of flip-flops connected to at the input of the multiplexer. At the input of the multiplexer. Here is the diagram representing a 2-input lookup table. 2-input lookup table. So 2-input lookup table means, of course, here 2 power n inputs are there. Assume that initially it is a 2-input lookup table. So it has 2 flip-flops with 2 flip-flops at the inputs of 2 by 1 multiplexer. 2 by 1 multiplexer. Of course, here 2 power n inputs means n select line multiplexer is there. Okay, so the multiplexer is 2 by 2 to the power of n to 1. Okay, so this is the general structure for the lookup table. General structure for the lookup table. So with this lookup table, okay, so you can realize whatever the logic function we have. So how the realization means? By changing the values in the flip-flop, the realization of lookup table can be changed. Okay, so let us see some of the lookup table designs for different different Boolean expressions. Coming to let us see here implementing 1-input combinational circuit. 1-input combinational circuit means, 1 input means the combinational circuit or the Boolean expression which consists one variable. Okay, so in this case, in the one variable case, the multiplexer size is 2 by 1. So since 2 inputs the multiplexer has, therefore 2 flip-flops you have to use. Each flip-flop can store either 0 value or 1 value. Okay. Now for realizing a NOT gate, 1-input lookup table is considered. Say, see here, so the data in the RAM is, or in the flip-flop is like this. In the first flip-flop the value is 1, in the second flip-flop the value is 0. Okay, and let us see what will happen. The operation is, suppose if the x value is 0, so what is the expected output? Y equal to 1. Okay, suppose if the x value is 1, y equal to 0, that is second input is connected. Since it is a 2 by 1 multiplexer, okay, if the select value is 0, the first input is connected to output. If the x value is 1, the second input is connected to the output. So the output is always complement of the select value, that is x value here. Okay, so that this particular lookup table realizes the NOT gate action. Okay, so similarly you can see the different realizations. So this is the diagram representing 2-input combinational circuit. So 2-input means 2-input combinational circuit means it has two variables x and y. Okay, x and y. So that 4 by 1 multiplexer you need to use. So with 4 input means 4 flip-flops you have to use. Okay, so under 2 variable any logic function you can realize using this structure. Okay, so similarly And if you observe here, this is the realization of lookup table for different gates like OR gate, NAND gate, AND gate, or XOR gate. Okay, like that other gates also you can realize. Okay, so see, the circuit is the structure, basic structure is same, but how the same structure can show different gate functions means by changing the values in the flip-flops. What I said previously, so changing the values in flip-flops changes the realization function by the lookup table. Okay, similarly, so if the data is in flip-flops 0, 1, 1, 1, it shows OR gate action. If the data is 0, 0, 0, 1, it shows AND gate action. If the data is 0, 1, 1, 0, it shows the XOR gate operation. XOR gate operation. Okay, so like that, based on the data stored in the flip-flops, the realization can depend. Okay, so like that the lookup tables can be realized. So and now if you see, this is the 3-input combinational circuit, the lookup table which is used to implement 3-input combinational circuit. 3-input means, combinational circuit means, that is the Boolean expression which has 3 variables. So such a networks can be realized using this one. Okay, so like that the different lookup tables you can observe for realizing different logic gates. Okay, in next class you can see the rest of the blocks.